So you don't have to worry about any formula. Alright?
Was example 6.1 finding the ratios of masses was at the final step. Changing mass over the total value.
Change in mass.
Over the total value.
The total mass is the mass of the spacecraft.
That was the final step.
That was it, yeah. So I'll do another problem in that and it will help you understand, okay? Now, a satellite traveling 8 kilometers per second question. Satellite traveling at 8 kilometers per second at perigee. Okay. At perigee altitude of 500 kilometers. Fires a retro rocket. What's a retro rocket?
Rocket is this retrograde.
Huh?
Rocket is this retrograde. Is that what it's saying? Going opposite direction.
Yeah. So what is a almost all rockets are retro rockets, right? Is that a statement, a correct statement? When you are used to aircrafts, you will rarely find a non-retro booster or a rocket in aircrafts. What's the biggest difference between a shuttle and an aircraft? The space shuttle and
The space shuttle doesn't have engines to actually take off from
kind of, well, that's not exactly true. It could take off from the. Yeah,
You said what's the difference?
yeah.
One's trying to escape the atmosphere, one's trying to this way.
But we know they fly in the same way, at least characteristically. They both use flaps, they both use control surfaces.
One uses rocket for
Yes, that's true. It's kind of true in that one does not have there is no turbines on shuttles. You see? There is no engine. There is engine, but it's not a jet engine. It's a booster or a thruster engine. It can take off. It's just not sufficient. The boosters are just not sufficient to get it out of atmosphere. Boosters are sufficient to get it in. Because when you're getting in, you don't really need boosters. You can slow down and then spiral. Okay. Now, do you have a non-retro rocket on an aircraft? When do you have a non-retro rocket? You know what a retro rocket is? Almost all rockets are retro rockets, right?
What is that?
What is the ratio, right?
Okay. So if your rocket is going this way, if the velocity direction is this, it always fires in this direction, right?
So if you're trying to go in a different direction, actually in orbit.
So if in orbit, what happens is, you typically do this to increase the velocity or increase the orbit size.
Yeah.
Now a rocket could be going like this, Okay, and it may fire in this direction as well. Or there is no head as such for a spacecraft. Does that make sense? Strictly speaking, there is no roll pitch yaw for a spacecraft.
Isn't it though?
But didn't we have a whole lesson on roll pitch?
Well, all it asks is, I mean, they're going in a specific direction.
So what? How do you define the pitch?
In relation to
Are we not?
Oh, I do.
Stuff like that?
In relation, think about it. In relation to
So
in relation to the direction of motion of an aircraft, the nose is always in that direction, right? Is that,
I think why not?
it's facing forward, right? It's always facing for an aircraft is always facing forward.
Right.
Does that make sense? Unless it is stalling, then it is not facing down. It is not facing forward. Does that make sense? When it stalls, what happens? There is no, the nose is up, but it is coming down.
Yeah.
Right? A spacecraft, there is no nose as such. A spacecraft, a space shuttle may be like this, right? Maybe like this, but it may be moving like this. And it's perfectly normal for a spacecraft to do that. It's not perfectly normal for an aircraft to do this, right? So, strictly speaking, what is roll pitch yaw? It's defined in the direction of that. But if this itself becomes irrelevant,
couldn't you base that off of the direction of the thrust of the spacecraft?
you don't base it off the direction of the spacecraft, you base it off the direction of the velocity of in which it is going, okay?
Right.
So essentially, it makes the same maneuvers as roll pitch yaw. You can't actually control that.
It cannot say, for example, you cannot really define the roll pitch yaw maneuver. So if you say roll pitch yaw maneuver, you're going to define it with respect to the orbit. You understand? Pitch is essentially the velocity direction. But at that point, how the spacecraft is oriented also matters. Does that make sense? In an aircraft, it is pretty much assumed that if the velocity direction is this, the orientation is also that.
So would you define roll pitch yaw as a Lagrange point?
Well, we don't have to go to Lagrange point. Even if you look at any orbit, the roll pitch yaw is defined as this is the velocity, right? If it's orbiting like this, then the tangential direction is the velocity. Any orientation change about that is pitch, okay? And this is the nadir direction, the one pointing towards Earth. Anything about that is, in fact, that is the pitch, okay? This is the roll, and this is the tangential, the local, vertical, horizontal. This is this thing. This any maneuver like this would be. But the spacecraft orientation may be completely random about that pitch, roll pitch yaw. And when you define your roll pitch yaw, when you send the command, the spacecraft will understand that command in the context of itself, not necessarily in the context of the orbit. Okay? So here, when you fire a retro rocket, the speed will increase. Okay? What delta V is necessary? This is the thing. To reach a minimum
That's all.
altitude of 200 kilometers. During the next orbit. How do you go about doing this problem? Anybody? This is the very simplest of the impulsive maneuvers. First of all, one of the things I'm going to ask you is graphically represent this problem. So you should be able to draw this and show me graphically what it's doing. Okay? And then be able to
Can we just use your
Hmm?
your delta N over N brother?
Can you do that?
We have, I think so. The ISP would just be the thrust over the altitude variables.
Delta N is not. I'm not asking for delta N. Okay. Yeah. Here, so what is happening is what is delta V? What is here? Think about this. You have this orbit, okay? Are you given what orbit this is? Is it a circular orbit? Is it a... Now don't assume it's a circular orbit. Don't assume this is this a Hohmann transform? It's not a Hohmann transform.
There's only two like.
There's only one more. Look at it.
So we don't assume that it's already like done a maneuver?
All it says is a satellite traveling at 8 kilometers per second at perigee altitude. Okay? So this distance is 500 plus
The radius of the circle,
okay,
Yeah.
kilometers. What is the velocity here?
8 kilometers.
8 kilometers per second. Now,
So this is the picture that we should draw. You know, just to graph this.
this is the initial listing. Okay?
Right.
What is it doing? In which direction will the rockets be fired? Hmm?
The right is far as that.
Oh, they're gonna go with this
It'll be far from here.
towards this.
It will be fired here.
I mean, they're gonna be coming out, but they're already far.
The rockets will be fired in this direction. The velocity will decrease, and when it decreases, so keep in mind it cannot reach 200 here. Okay? It has to do this. This is what?
Oh,
200. So this distance is still, it's immaterial what this distance is, okay? But here when it fires the rockets in this direction, the speed will be less than 8 kilometers per second.
So last time when we were looking for
Hmm.
the altitude,
Hmm.
what was the reason that we didn't have to add the 6.
Here, you still have to add this 60.
So,
Will that 200 become the new perigee?
It's the new perigee.
so we're trying to lessen.
Yes. So here you can go from, see, I talked about going from this orbit to this orbit, right? How do you go? You go like this, right? You realize you can also go from this orbit to this orbit. What do you do is, you fire your thrusters here, it will get into this orbit. It will get into this elliptical orbit. Does that make sense?
So you'd also have to slow down.
You have to slow down here. The second maneuver will be, the first maneuver will be, this is let's say V1, okay? The second maneuver, you have to decrease the speed by, this is Vp. You have to decrease the speed by delta V. So it's actually in this direction. So if you want to get velocity in this direction, you fire the thrusters in the opposite direction. And you get into this transfer orbit. And when you come here, this will be VA.
So you fire in the opposite direction or slow it down.
Right. And let's say this is, you fire this one, this is delta V2, and this is V2.
Is that why the problems they would add in that retro comment?
Yes. Okay. So here, you can assume this is circular, but the transfer orbit is definitely not circular. Okay. How do you go about computing this? That's the question. Does this problem make sense? You can go from here to here through this transfer orbit. But you can also go from this to this through this transfer orbit. Does that make sense? Boris?
Yeah.
So we're doing the opposite of that up there in this box.
Here is the same thing. So what is happening is, huh?
Nothing like that.
I'll just redraw this. You are in a 500 kilometer circular orbit, okay? Your goal is to get to an altitude of 200 kilometers. You with me? It says this is the perigee, okay? This is P. And what is this distance? 500 plus 6378 kilometers, okay? This is, how much is this? Let's say V1, 8 kilometers per second. Okay. You need to keep in mind, in just one maneuver, you cannot get into this orbit in just one maneuver. That's just not possible.
Yeah, don't you know, like, more than two, maybe?
Yeah. At least 2 maneuvers. You understand?
Correct.
So one point is always going to be common when you do a transfer for an orbit. Okay? So here, either this point is common, either you do the maneuver here, you do maneuver on any point. That point should be
Common point.
perigee. You got it?
So whatever point you choose to fire from is your perigee.
Is the perigee. Okay. So when you do the perigee point, this is the perigee for the initial orbit. Alright? So now what you do is you have to decrease the velocity by a certain delta V. You got it? Then the velocity, this will be the V A. Think Y. Okay? Because you are decreasing. You get it? So your orbit, the transfer orbit would be you get it? What is this distance? This is still the focus, okay? What is this distance? 200 plus 637.
That's what I, once you find that number, will that be the number we use to like calculate like the new perigee, or would we still use
And that's what I'm doing. Okay? Now, what is asked of you is what is this delta V? You get it? What is R1? Huh?
500 plus
6878?
Is it 6.8 or 6.3?
Oh, I'm sorry.
What is RA?
200 plus.
No.
6.5, 7. Just add 1. Wait. That's going to be the new apogee.
Yeah, it's apogee, right? Here we are decreasing, right? RP is what?
Because we chose that.
Oh, it's going to be 6, 5, 7, 8. These are good. We changed our order.
You got it? These are the parameters for transfer orbit. This is the parameter for initial orbit. Okay. What is V1?
8 kilometers per second.
8 kilometers per second, right? What do you need? You need VA. There is no V2 because the second orbit is not a circular orbit. Does that make sense? The velocity is constantly changing here. Here the velocity is the same. What is VA? I gave you this formula yesterday. You got it? H, yes.
You said you're going to give the formulas for this, or that includes like the small parts like that? I mean, if you say
I'll give you this. I'll give you V is H is equal to RV. Add perigee and apogee. I won't give you the steps. So you should be able to apply this here. Okay? So here h is always constant, guys. At any point h is constant. The r increases, v decreases. V increases, r decreases. So h is always maintained constant for an orbit. What is h? ht. Here you understand what ht is, what it denotes. Angular momentum. I gave you this formula as well. Got it? So from this you can calculate. Do you know RA? Do you know RP?
Yes.
Do you know mu?
Yes.
You can calculate age, right? Once you calculate age, you can calculate. You know this. You know VA. What is delta V?
Yeah.
You should know which one is greater. Okay. What happens if you do the other way around? You'll go in a bigger orbit. Okay. This is the orbit. Yeah, I want you to sketch like this, because see, when you sketch this only, like whatever Kenneth asked, just doing this, unless you do this 100 times, you cannot just use the formulas and calculate. If you sketch it something like this, you really know what there's only how many formulas are you using here?
3.
Only 2 formulas. Everything else is known actually. 3 formulas.
Yeah.
Using this,
Yeah.
this, and this. I'm not going to give you this formula. Please don't expect this formula. Kenneth. Does that make sense? I need you to understand this. This can only be understood by sketching.
First question. VA is like the final velocity. So why isn't VA minus V1?
It is decreasing. You're going into a smaller orbit. Keep in mind, these 2 numbers are very critical. What orbit are you going into? You're going from a 500 kilometer orbit to a 200 kilometer orbit. If you were going to a higher orbit, what will this point become? Guys, this will be a question in the exam. Okay, keep your cell phone down. I may ask you this simple question. If you are going to a higher orbit, this is the green is the initial orbit. If you are going to a higher orbit, what will that point become for that higher orbit? Perigee. No.
Are you asking like blue to green?
No.
Green to blue.
I'm in the green orbit, okay?
If we were to go bigger than that,
If I go to this orbit,
then we can.
It's still gonna be the same point.
Yeah, that's
it will become the perigee of this orbit.
Yeah.
If I go to a lower orbit,
That's the
that will become the apogee
So it's,
of that lower orbit.
so VA would change to VP.
For this red,
Or we subtract VP then minus V1.
then it will be VP, VP minus V1 will be delta VP. Because VP is greater now. You understand? If you decrease the velocity, you get into a lower orbit. You cannot get rid of this point. Okay? So how do you spiral in? What is spiraling in?
Sorry.
you decrease velocity here. Okay, you get to this point, you decrease velocity here. It will become.
That'll become your
It will become this. You decrease velocity here, you become this. You decrease velocity here, you become this. You decrease velocity. That is how you do it.
So how do you ever go circular?
Huh?
How do you ever get in the circular orbit then?
You need two.
You can do circular if you're doing this. You just do. This is your this thing, right? You decrease the velocity, get the circular orbit.
Either that or how much you're decreasing.
You cannot go from one circular orbit to another circular orbit in one maneuver. Does that make sense? It will always be a elliptical transfer. One circular to another circular is always a elliptical transfer.
If you are already in an elliptical orbit,
Then you can go into a circular orbit. You can go into a. If you're. Here is the thing. This is your orbit. Elliptical orbit. Okay? What is this point? This is the focus. What is this point? Perigee. Right? If you do a perigee maneuver, you get into a lower orbit, lower circular orbit. If you do a apogee maneuver, you get into a bigger circular orbit. Does that make sense? You do a apogee maneuver, this becomes the radius of that circle.
Right.
You do a perigee maneuver, this becomes a radial. So you will get a smaller circular orbit. If you do a maneuver here, you get a bigger circle. Okay? You'll be able to solve this problem in the exam.
So, in this problem that we did before, we went from the green to the blue, so that's the reason why we did the velocity at the apogee instead of the VA. Kind of did the last one.
Now, from going from this to this,
Oh, I mean, you went smaller, so you did the area, but it's still VA for whatever reason. Okay.
If you want to get down to
And you could change from V1 to V8.
Hmm?
You could change from V1.
Can I take pictures of it?
So, what circumstance could that become like V1 minus VP?
if you're going to bigger, if you're going from green to red, if you're going from green to red, right, what is going to happen? You're going to circle a larger orbit, right? That time, see, this thing is V1, and then you have to increase the velocity, right? By a certain delta V to get into this orbit. Does that make sense? What is this?
That's it. So, that would be VP then,
VP.
because you're doing the apogee.
No, you're doing a perigee maneuver.
So, you can do a perigee maneuver to go smaller and a perigee movement to go larger.
No. This, before you do the maneuver, this point is just a point. Only after you do the maneuver, this becomes the perigee. This is the perigee of what?
Red,
This one.
blue dotted line.
Gotcha.
You got it? That becomes the perigee. This becomes the apogee when you do the, for this orbit.
So that's
For
why-
this orbit, it is still the perigee, but it is V1, right? Since it's a circular orbit, it doesn't matter perigee or apogee. It's the same thing. You get it?
So when we go green to blue, then it's going to be apogee. Well, it'll be
Green
the
to
perigee,
blue, you're right. Green to blue, it will become apogee.
Right.
From green,
Green to red, it will become perigee.
alright, from green to blue, the perigee becomes the apogee.
Yes,
Oh.
that is a true statement. But if you should understand that, because the perigee becomes apogee. You're right.
That's why you do VA.
Huh?
That's why you put it.
That's when you do V. It's just a matter of understanding.
It's an automatic question.
Yes.
I mean, it's the same question I already asked, but I'm asking you. VA is the final velocity. Once you get to, so in V1, it would be a negative change in velocity. So why would you do the VA minus V1? That's what I just don't get.
I'm not doing VA minus V1, I'm doing V1 minus VA.
V1 is the
It is less. I'm decreasing. VA is less than V1.
He's saying he's gonna decrease the velocity, it won't be a negative.
He's saying that you have V1 first,
Hmm.
and then, what did you say?
If VA is the final velocity, if VA is the final velocity, you always it seems like that you do final minus initial most of the time for things like this, and you want the change in velocity to be negative because you change from something higher to something
There
lower.
is no, this delta V
Uh-huh.
is always, this is not a vector.
Mhm.
You understand? This is, there is no negative here. The direction in which you fire the thruster is. So here, where will the thrusters be pointed in this? If I ask you where the thrusters are pointed,
So you just want to find a relative change in speed.
relative change in speed. It is speed.
To go from the larger to small orbit, those are going.
Where will the thrusters be pointed?
Oh, well, that's pointed
Up.
So that is always going to be positive.
That is, yeah.
So
It's a speed. Is there a negative speed?
No, not that time.
You decrease the speed by so much, right? You don't increase the speed by minus 20.
Okay.
You decrease the speed by 20. You decrease the speed by delta V.
So I'm always going to write that in a way that makes it positive.
Yeah, if you get it, this is not acceptable. Because that will mess up the calculation of delta n. This, you'll get a negative number here, and then you do the same thing, you'll get another positive number, and then that will mess up the delta n calculation.
You keep the absolute value. of
You
that.
keep the absolute value. Yes.
Why don't you just now? Here, I got it.
So here we are not dealing with vectors. You have to, it is common sense, and it is your training to be spacecraft engineers, which should say that the boosters, the thrusters are pointed in this direction. And the delta V which needs to be achieved is this much. The change in velocity, change in speed. Got it? And it's also very, very critical that the thrusters are perfectly aligned like this. If they are off by a little bit, what's going to happen? You're going to get a different orbit. Okay? That's a whole other problem. That's the reason you should understand, you should appreciate what the InSight did or what are some of these missions do, especially the interplanetary missions. And you should try to participate, you should try to somehow be a part of that. It is true. And that is the reason it is called rocket science. See, this is just one aspect. Okay? And if you are given a vehicle and you're asked to align and then do this, it may take you decades together to get that accuracy. Imagine this is an autonomous system, you don't know where it is going, it's millions of miles away, and you're issuing a command, it is orienting, it is doing the perfect delta V, it is in perfect orientation, it is going to land perfectly in that spot on Mars where there are no rocks. And it is going to carry certain instruments. The instruments are not damaged. The environment is extreme environment, extreme temperature. All that is correctly happening. How many attempts did the InSight take to get there? One attempt. Yeah, that's how many Mars missions are failures?
We haven't failed, have we?
No failures.
I don't know.
Don't you want to be part of something so amazing?
Yeah, but I'm hoping to get that, so kind of.
So you're getting the foundation for that here.
So the first time you failed us, was the last time you do it.
Exactly.